No, it's okay. It'll be answered through now.
Yeah, so today I'm presenting my work on supernovae, particularly on one of them, supernovae 2017gax. And I'm just going to go through what these kind of supernovae are. They are the core collapse supernovae that come from stars that have lost their outer hydrogen and sometimes helium envelopes. And I have a cartoon. So for a high mass hydrogen star, they will be exploding as a non-stripped hydrogen-rich supernovae. If through some mechanism, which I will elaborate later, if the hydrogen is being stripped, then the supernovae is classified as a type B supernovae. If the helium is also stripped, then it becomes a type 1c supernovae. Here, both type 1b's and type 1c's are classified as stripped envelope supernovae. Yeah, so then how are these outer layers stripped? Well, theoretically, there are two mechanisms in which they can be stripped. One of them is through single high mass stars. So those high mass stars have strong enough winds that pushes out the outer envelopes away. So that is due to radiative pressure. And so for high mass stars of larger than, let's say, like around 30 solar masses, they'll be massive enough to strip themselves away and become completely hydrogen poor. And of course, binary interactions is also really important. Binary interactions can lower the mass needed to strip away their envelopes by a companion star. Several studies have shown that binaries is the main pathway in which this kind of supernova is formed, and there are a few evidence. So one of those studies showed that around 70% of massive stars will interact with the binary at some point of your lives. And around a third of core collapse supernovae are stripped. So here I have a pie chart showing all the colored portions are the percentage in which the core collapse supernovae are stripped. And this is a pretty high percentage. Through initial mass functions, we don't have that many high mass stars for them to go through self-stripping by themselves. So this means that batteries play an important role. And then thirdly, type 1bc supernovae usually have low ejecta masses, indicating that those progenitors are also lower mass. But then on the other hand, there are other studies showing these progenitors are still different from hydrogen-rich supernovae in a population level. One of these studies show that stripped envelope supernovae are correlated with younger stellar populations, kind of indicating that perhaps these progenitors are actually kind of massive stars. And then stripped envelope supernovae also have higher nickel masses than those typical regular hydrogen-rich supernovae. Well, it is not a one-to-one relation, but usually higher nickel masses indicates a higher mass progenitor star. And so what I wanted to show here is that there's still a lot of uncertainties about the exact details of stripped envelope supernovae progenitors. And one way to answer this question perhaps is by looking at the direct detections of the progenitor stars. So in some cases, there are serendipitous imaging of the supernova site before the supernova explodes. It's pretty rare, and for the stripped envelope supernova case, we only have 3 such candidates, and actually only one of them is a confirmed detection. Here on the right, I'm showing an example. So this is for supernova 2019 YBR, 2.5 years before the supernova. We have a HSC image on the explosion site, and you can see that there is some kind of detection of a possible star that is the progenitor star of this supernova. And moving on to the supernova that I studied. So 2017gax is one of the only stripped envelope supernovae to date that has both HSC pre and post explosion imaging. And as a spoiler, both of these images are not detections, but we're able to learn a lot of science through these images. And I'm going to show you how. 17gax is a type 1c supernovae, so it has no hydrogen nor helium in its early optical spectra. It is pretty close by, around 60 megaparsecs, and it's in a low extinction area. Here are some HSC images. So 12 years before explosion, we have imaging from 3 different bands, and all of them show no detection. 2 years after the explosion, if you look at this highlighted box here, there is some light remaining from the supernovae after the supernova explodes. And 3 years after the explosion, the light kind of, okay, it's hard to see here, but the light had expanded to a ring-like structure, possibly due to the sample. Then 6 years after the explosion, the light fades again across the 4 bands, so there's no detection again. Today, I'm going to focus on the first and the last few points. All right, so the goal here is that we want to know, like, on a HR diagram, which regions on it is the progenitor star and possible companion star allowed, and which ones are they not allowed to be in. To do that, I use a combination of stellar models. I use hydrogen-rich and hydrogen-poor models. So hydrogen-rich models because we assume that any possible companion star must be a main sequence star. And we use hydrogen-poor models because the progenitor stars of those supernovae is hydrogen-polar. Now I'm just going to go through my steps of what I did. I selected a synthetic spectra with like various temperatures and compositions. I would scale them to various luminosities. Then I performed a synthetic spectra to get a theoretical magnitude. Then I compared that magnitude with my HSD upper limits. So that was like a lot of words and probably confusing. So I have a visualization showing what I did. Here is so here are the 4 upper limits from the post-explosion images. So from post-explosion, we're able to explore like what kind of possible star the companion is. And to do that, we could draw a SED on top of the upper limits. So in this example, I use a 22,000 Kelvin spectrum model at this luminosity. And since the SED is above my upper limits, this spectra is not allowed. So this means that we need to rescale this SED down to lower luminosity. And here it's still not allowed, and now we have an allowed spectra. So this means that at 22,000 Kelvin, any star that is above a luminosity of log L over L sun of 3.6 would not be allowed, because anything brighter than that, we would have detected it in our HSD images. We don't just do it for 22,000 Kelvin, we do this across a range of temperatures on this HR diagram. And here I'm showing a HR diagram with some cellular evolutionary tracks. So repeating what I did before, I did it with across a range of temperatures. And here I'm showing the gray areas are the ruled out regions, and the yellow are places in which the companion star could be at. So so we can rule out main sequence companions with a luminosity of log L over L sun of 3.6. Now we also have pre-exploding imaging, and for pre-exploding imaging, it's more tricky because the progenitor star and the companion star are both inside the same image. But we start off with the same HR diagram, and we also do the same thing for the companion because the companion is also in the pre-exposure imaging. But for the progenitor star, it could be a Wolf-Rayet star. So in the high luminosity and high temperature region, we used a Wolf-Rayet star model. And you can see that we wrote out most luminous Wolf-Rayet stars in our pieces. So it's possibly the progenitor star is not a Wolf-Rayet star. And then the progenitor star could also be a helium, like lower mass strip star. So for that, we use a weak wind strip star model. And you can see that most of that box is like colored, meaning that it's higher possibility that the progenitor star is a lower mass strip star. And then here I'm just showing some example SEDs of a allowed Wolf-Rayet star and a helium star model. And the dark blue is the Wolf-Rayet star, and the dark blue is a spectrum for the helium star, and the pink is an example for the Wolf-Rayet star. So how does all of this tell us about like binary theory? And we can use these upper limits to in a context of binary population synthesis models and learn some things about the evolutionary histories of strip and supernovae. So to do that, we use one such binary population synthesis model called Poseidon. Poseidon is a really detailed stellar evolutionary structure of binary evolutionary code, and that it doesn't use lookup tables or interpolation. Instead, it self-consistently models the stellar evolution. And what it does is that it can tell us what combinations of progenitors and possible companions are expected to go strip level supernovae. So for that, we considered both the progenitor and companion together by adding up their spectra, calculating the sum spectra as synthetic photometry. Then any system that is brighter by that combined magnitude will be ruled out. So basically, we start off with over 16,000 possible systems that will explode as a type 1b supernovae. And here, the dark gray are the progenitors, and their corresponding companions is colored as lighter gray. So after we kind of implemented the HSD improvements, we found that only around 0.5% of those systems are allowed, and they're plotted with like the dark blue diamonds, which are progenitors, and these are the companions. Additionally, we also have some constraints on the progenitor radius and the ejected masses through direct modeling on the light curve. So this analysis is done by someone else in UC Davis, but applying those additional explosion constraints, we're able to further narrow the percentage down to around 0.3%. This seems too good to be true because we only had non-detections and we're able to like kind of pinpoint where the progenitor and companion stars are to such a narrow range. So why is that? It turns out that Poseidon had been predicting systems without preferred ejected masses to a really high luminosity area. So it's saying that the stars in this pink color, they will explode with a ejected mass within like our preferred region, and they're so luminous, but we don't really observe such a luminous star in our HSD images. But this shows like one of the caveats that Poseidon has, but still like considering those caveats, we can look into some examples of systems that are allowed with our constraints. So one such type is when here I'm just showing an example of one of those types. So here, the exploding star could be the primary star, meaning that the exploding star started off as a more massive star in that binary system. And here, after the core helium burning, the primary star expanded, and some of that material is gravitationally pulled towards the companion star. And then something called a common envelope forms, and then a common envelope is ejected. And in this process, the mass transfer is really inefficient. And then the primary star becomes a strip star before exploding into a strip of supernovae that we could observe. Then the other type of system is when the exploding star is actually the secondary star, meaning that it is the second supernova that had exploded in that system. So this allows the primary star, so the first star that had exploded, to be really massive. And it could be that massive because it is now a compact object, so it no longer contributes to any light in our HSD images. So here I have a cartoon of what I mean by that. So the more massive star first expands during shell helium burning, and some of that material is transferred to the companion star. So now the more massive star becomes a strip star before exploding to the first supernova in our system. And then this one becomes a black hole. Then the secondary star, which is the lower mass star, it also goes through shell helium burning, loses some mass through binary interactions, and then it becomes another strip star that exploded as a strip emerald supernova that we observed. So that was like one object study. In the future, we're going to expand this one object study to a population-wide study. So we're going to analyze all the strip emerald supernovae that had HSC images before the explosion. And this is pretty important because now we only have 3 candidates. So if we included all the analysis with the upper limits, it's going to tell us a lot about the population. Something else is that, and there are some uncertainties in binary evolution, and we're trying to use this kind of observation study on population to constrain these uncertainties in binary evolution. So what I mean by that is that we can use these observations to test out uncertainties in binary population synthesis models. For example, earlier I showed that Poseidon was like predicting those stars to explode at really high luminosities, and maybe there's some errors in its modeling. Yeah, so that's it. Thank you. Yes.
Right, of course, always very happy to see binaries and strip stars. In your very first picture, you showed actually where the star was. It didn't look like it was very close to any of the arms of the spiral galaxy. Has anybody tried to look at kind of population it's in?
So keep going.
I think you just one forward, this one. Yeah, I mean, it doesn't look like it's close to a star forming region or anything obvious, at least like that. Is it in a young population? I ask in part because I think that may be relevant for your second solution, is that the Crab pulsar is very weird. It's well above the galactic plane, so not near star forming. There's definitely no surviving companion. It's absolutely a stripped supernova, probably low mass. It seems sort of similar to this. And I think one of the solutions for that is indeed that your second suggestion, that it went up there with an already compact companion. Anyways, maybe something to look at whether you have extra information from where it went off, what kind of population the star went off.
Yeah, sometimes there are papers that also look into like place age constraints by like modeling the turn-off point. We haven't done this for this supernova yet, but I think that's something that we could do.
Yeah, I think there's some stuff around. I agree with that.
Very nice.
Yeah.
Great talk, Jerry. I was wondering, and maybe building off Martin's question a bit, is how can you tell which scenario it was? Is there something that you can tell if it was second supernova in the system or the first? And we should expect the second, and how long after with the second?
I guess the first example, so it's more probable for the first one because there are like less systems with a higher mass star, like probability wise through Poseidon, we found that type 1 systems, there are more type 1 systems than type 2 systems. Yeah. But yeah, it's hard to know like which example it is. So I have a figure here, like sorry. Basically, even if you have detections, there are also papers that have like contradicting opinions. Like some papers would say, oh, that's a Wolf-Rayet star, but then another paper would say this paper is a Wolf-Rayet star. So I guess even with detections, it's hard to tell. Yeah. Yes.
If you go back to that example too, just the diagram. I was wondering, do you necessarily need to form a black hole in the scenario, or can it also be a neutron star? Or just any compact object?
Yeah, so I guess it could be any compact object. And just in this example, I was looking at one like particular example in the like 16,000 in the allowed examples, and then yeah, I just plotted one example of the black.
I think you're right that they have to be rare because we don't see many double mutant star binaries. There are lots of binaries get disrupted at the first
so this
supernova.
one is disrupted, and then this one we found a lot more.
Oh yeah, that's right. You have one day. Yes.
Thanks, Jenny, again.